So we've already seen that tree diagrams work for organizing and visualizing the different steps in a multiple step probability experiment. But we'll actually see we're building towards being able to use them more effectively for a specific kind of situation. And before we get to that, we're going to add another layer to what we already know. Like we've already seen them as a way to manage our list of outcomes. Today we'll look at using them to calculate probabilities and multi-step probability questions. And that'll lead us to being able to manage the addition of multiple favorable outcomes to get us answers to more complicated problems. Before we get to that, we're really going to focus on the second step here of calculating multiple step probability, which is something that you can do without tree diagrams. But again, if we want to build that last ability to get answers to tricky questions, we're going to need it. So here's how to calculate with tree diagrams. First off, you got to build a good tree diagram. Here we're talking about a problem where Butch Cakes spins the show and spinner and flips a coin, and we're asked to make a tree diagram, probability tree, that shows each outcome, but also calculates, you see here, calculate the probability of each outcome using the tree. So we start out, as always, with our omega symbol. That's indicating to us that we're starting with all the probabilities, all the possibilities wrapped up in one, and then we branch out of that, right? And each column that we're going to show here is going to be one step in the experiment. This experiment is spinning the spinner first and then flipping a coin. So we're going to have a column here. Everything showing up along here is going to be spinning the spinner. And there are 4 possibilities for that. It could be red, teal, yellow, or blue. And then after you've got that first step, you have the second step, which will be showing up in another column here. That's flipping the coin. So out of each of these first outcomes, you're going to have 2 possibilities, either heads or tails, growing out of those. And that gives us a total of 8 outcomes if we count the ends of our branches here, which if you use the basic counting principle makes sense, right? 4 possibilities in the first step, 2 possibilities in the second. 4 times 2 gives me 8. So far, so good. And then finally, we're going to list all those outcomes just in a little abbreviated form in parentheses, right, showing the 2 steps. So, for example, if I want to show red as the first step, outcome, and heads as the outcome of the second step, I'd write that just either as red, comma, heads, or R, comma, H. Likewise, red tails, I'm going to write as R, comma, T, and so on. But I don't want to just come up with a good tree diagram like I've done here. I want to then actually use it to calculate. So this is what's new. And the way you calculate is you go back to each of your branches throughout the whole diagram, and you adorn them with the probability of that outcome in that step. So for example, if you look at getting red in that spin, right, that's 144 degrees of redness out of a total of 360 degrees if I think of the whole circle. So it's 144 out of 360, which I can write as 4 out of 10. Now you might say, well, couldn't I reduce that fraction to a little further to 2 out of 5? Wouldn't that be the properly simplified fraction? Yeah, and this 2 out of 10 here, this could be a 1 out of 5 as well. But you'll see that there's an advantage in this specific type of problem to not fully reducing, and just reducing to the point, just simplifying to the point where each of your probabilities here has the same denominator. You can still have these over 360 as well, but I like these numbers better because they're easier to manage. Down here, again, if I'm writing the probability of getting heads, I don't have to start thinking about, well, do I combine this with that to do the calculation here? No. Just along here, I'm just going to write what's the probability of getting a result of heads on this flip right here. So that's just 1 out of 2. And it's the same for all these. It's always 1 out of 2. And since I've got all of my branches on my probability tree, they now have probabilities written in on them. If I get to the end here and I want to calculate the probabilities of each of these outcomes, you can go back through and say, okay, if I want to calculate just the probability of any given outcome, I can travel along the branches that lead me to that final outcome. So if I want to find teal then tails, I would say if I start at omega and I end up at teal then tails over here, let me see the fractions I would collect along the way. 1 over 10 and 1/2, and those are going to be the fractions I'll multiply together to get my probability here. And that's the same for all of these, right? 4 out of 10 times 1/2 would give me red then tails. 2 out of 10 times 1/2 would give me yellow then tails. All these probabilities work out that way. Now I mentioned that it's advantageous to keep all the probabilities for a step in the same denominator. That's because when you get to the end, if you've done that, you'll see that all of your final probabilities, which again aren't fully reduced, this could be reduced, this could be reduced, this guy up here, this guy up here, I've got them all in the same denominator, which means it's easy for me to add them together. And the reason why I'd want to do that, or I'd want to be able to do that, is if I add them together, if I've done all my work properly, I can add them together and they should add up to 100%. They should add up to a total of 1. So 4, right, for this guy, plus 4, we're at 8, plus 1 is 9, plus 1 is 10 out of 20 so far, 12, 14, 17, 20 out of 20. That's a pretty good indication that I've done my work properly. And that's just a handy kind of fail-safe to make sure you've done the work well. If a question's asking you for a final answer, of course, you're going to simplify and reduce your final answer. But along the way, it's for keeping track of your work, it's easier if you don't. All right, let's do another example, because the more examples you do, the easier it is to understand. Let's say Garrow's got a regular 52-card deck that has face cards and number cards. And we're going to include aces as number cards. I think it was the number 1. So he draws a card. He observes whether it's a face card. And he draws a second card without replacing the first one. And he observes whether the second card is a face card or not. Now, calculate the probability of each outcome using a probability tree. Notice here, this is a case of dependent probability, because when you draw that first card and you don't put it back in, it's without replacement here. That means the second step is going to be affected by what happened in the first step. So let's see that in the tree diagram. All right, we still start with our omega. We're starting with everything. Then the first step in the experiment is drawing a card and seeing whether it's a face card or a number card. And we build our tree diagram further. Out of each of these possibilities, we grow another set of possibilities. If I got a face card, I could get face or number in the second time around. If I have a number card, I could get face or number the second time around. And each of these outcomes shows up in a column at the end. Face, 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 number, number, face, number, number. Now, what I got to do to calculate this probability using the tree diagram is I go back and along each branch, I write in the probability of each of those outcomes in that step. So in the first step, there's 12 face cards out of a total of 52 cards. So those 12 out of 52 would give me a face card, and the other 40 would give me a number card. Now, this gets a little more complicated in the second step because of the dependent probability, because I'm not replacing here, right? If I did get a face card the first time around, then that means there's only 11 face cards left in the deck, and the deck only has 51 cards. Of those 51 cards, 11 are face cards, and 40 are number cards. So this probability here is a little more complicated than the last question we saw. Down here, if I got a number card the first time around, now I've got 51 cards left in the deck because one of them's gone. And of those 51, 12 of them are face cards, 39 are number cards. So those are the probabilities down here. And again, if I want to do the actual calculation of probabilities of these outcomes, I go along the branches and I multiply together the fractions that I hit along the way. If I want to find the probability of number card then face card, that would be this fraction, 40 over 52, times this fraction, 12 over 51. And again, since I haven't reduced these, which I could do, and the numbers here are kind of very big, I can add these together, and if you add all these up together with your calculator, you'll see that they do add up to 2,652. They do add up to 100%. And that is how you calculate probability